I would like to thank the sponsor of this video, Statistics.com, who has been educating students and professionals in data science from all over the world for over 20 years. But more about that later. Let's get started. Hello and namaste. My name is Brandon, and welcome to the next video in my series on time series. In this video, we will go over basic concepts and walk through the Naïve forecast, which is the most basic forecast, using an example. So, as always, like, comment, and subscribe, and let's get going. So first, let's take a step back, a few steps back, actually, and think about what we're trying to do here in time series forecasting. So time is persistent, and in this case, we have a series of data points that are evenly spaced in the same units over a period of time. And we are trying to forecast what will happen next. So will the value be up near the top, be near the middle, or near the bottom? So that is the larger goal of time series forecasting. Time series analysis falls into two broad categories that sometimes overlap: predicting and modeling. So in predicting, we're just trying to figure out what will happen next. We're driven solely by the data we have at hand. We are not interested in why that is the case, what factors influence that value, any of the history, trend, seasons, other variables, or anything like that. We're only using the data we have to predict the next value. In modeling, it's much more complex. So we want to know the how and the why. We want to know how other variables might influence the next value in the time series. We might look for seasons and trends. We might look for explanatory things outside of the time series itself. Could be economic factors, could be other weather factors, it could be anything. So we're trying to build a more complex model that will allow us to forecast further into the future and, most importantly, be able to explain why. One quick example of the difference here is that I keep track of the energy usage in my home. So just using the data, what I'd be interested in is how much energy I've used over the past 7 days, past 30 days, whatever, to try to figure out what tomorrow's usage might be. If I were doing modeling, I would build a massive model that keeps track of other variables. So what day of the week is it? What is the temperature outside? Was I home or not home? Was I doing laundry that day? Or what have you? So in the model-driven approach, I would keep track of all that other data and then try to explain why the next value is what it is. In the data-driven approach, I'm not doing any of that. I'm just looking at the past, 10, 15, maybe 30 days and building a prediction just based off that data alone. Another broad way to think about this is known versus unknown. So in this case, for time series, the past is known. We have the data for it, whereas the future is unknown. And to the extent that we can know the future, we know it less the further out into the future it goes. Certainty versus uncertainty. So the past is certain because we have the data for it. Now out into the future, we have increasing uncertainty the further out we go. So yes, we are uncertain about the next time period, but we are even more uncertain about the 10th time period or the 30th time period after now. Testing versus predicting. So the past data that we have in our time series is used to test several methods to minimize forecast error. Then we use that method or methods to make predictions going into the future. Now, of course, the predictions we make into the future, the farther they go, the less certain we are about them. So we can think about time series forecasting in several ways. And these are just some broad heuristics we can use to think about what we are doing in time series forecasting. So let's get into the process. The simplified prediction process, and this is simplified. Step 1, gather time series data for a time period. Now be aware of stale data. So stale data is data that, yes, goes into the past quite far, but it may negatively influence our time series forecast if it is no longer relevant, or if something changed since then. For example, in financial forecasting, it's usually standard to use the past 5 years of data. That can be 60 monthly measures, or we can do it weekly or even daily. Usually it's 60 monthly measures that are used in financial forecasts. So beware of stale data and only use the data that's relevant to the forecast that you want to make. Step 2, select appropriate forecasting methods for the time series data. Not all methods will be appropriate. Step 3, apply those forecasting methods to the known time period that we have in step 1. So this is a form of backtesting those several methods that you selected in step 2. 4. Evaluate the forecasting performance of each method for the known time period. So as you can see here, what we're doing, we are matching forecasts that we make with evaluation methods and then evaluating them on that criteria. Step 5. Use the method with the lowest forecast error to predict values into unknown time periods. And this next part is extremely important. Under the assumption that future conditions will be like the past conditions upon which the time series is based. So this is all in the context of the assumption that the conditions that were present when the data was collected or happened in step 1 will be similar to future conditions. If something fundamental change or large changes, then the forecast is not going to be very relevant and of course not very good. Step 6. Note, certain data-driven forecasting methods can only forecast one period into the future or where all forecasts are identical going forward. The forecast line is just a flat line straight into the future. The main reason for this is that in data-driven methods, you will eventually run out of data. So for example, like a moving average, eventually you're going to get to the point where you don't have any more data from step 1 at the top, and you can't go any further. And what happens is you just stop there, or you take that last value you forecasted and extend it out into the future indefinitely. And of course, we will talk about that more in future videos. This is different than in model-based forecasting. So in model-based forecasting, we can forecast out into the future pretty far, but keep in mind that of course, those forecasts will be less certain as we go into the future. Step 7. Some forecasting methods have parameters within them that need to be chosen and optimized. A few quick examples of this are moving averages. So we can select the time period for the moving average. We could have a 3 time period moving average, 5 time periods, 10, 30, or whatever. We could also have weighted moving averages. So we can apply weights to those different moving average periods. So if we have a 3-day moving average, we could put 50% of the weight on the most recent data. We could put 30% on the data before that, and then 20% before that. We could choose whatever we want. Final quick example is in smoothing. There's a smoothing parameter we have to choose. So even within each method, some of them have parameters to choose or optimize to make sure the forecast error is as low as it can go. So in essence, the forecasting process is somewhat trial and error. Assuming future time periods will be like past time periods, we are matching the best method or the lowest forecast error with the past, then forecasting using that method going into the future.
This is Business Analytics using forecasting.
Hello, and welcome to Persuasion Analytics.
I will be your instructor in the next 4 weeks as you learn about interactive data visualization methods.
This course will be an exciting opportunity to learn about and play with modeling that's influencing our daily lives.
Data and statistics touch every facet of our lives. In fact, that is why you are here on my channel. Statistics.com is committed to preparing the next generation of data analysts, just like you, while being human-centered. And, depending on your school, you might even be able to earn college credit. Classes are relatively small and personal. As a student, you aren't just a number. You can ask questions directly to your instructor, who, quite often, literally wrote the book, and receive a quality education with a personal touch. Statistics.com was the first online education institution approved by the American Council on Education. In the beginning, only 1 course was offered. Now, 75 courses are offered, covering the gamut of data science education. Many students are working adults from all over the world, and because courses are offered asynchronously, students can still maintain a career, family, and personal interests while also studying what they need to learn to take the next career step as a data science professional. For more information and a special discount offer from Statistics.com, please see the description below. Now, back to the video. Here is the generic forecast accuracy matrix. So it looks like this. In the left-hand column, we have 5 methods. Method A, B, C, D, and E. And those methods are used to generate the forecasts. At the top, we have evaluation methods. So method 1, 2, 3, 4, and 5 in this example. So what we are doing is matching each forecast method with an evaluation method. Therefore, it's a two-step process. Step 1 is to generate the forecasts themselves, and then step 2 is to evaluate those forecasts for their accuracy, which means minimizing forecast error. So in general, the goal is to minimize the forecast error for the known time series. Then, use that forecast method to make forecasts for future unknown values. Now, not all forecasting and evaluation methods are appropriate or even possible for data with certain characteristics. For example, data or errors that have negative and/or values of 0 will be inappropriate for certain methods. Evaluation methods are sometimes in different units. So it can be in the original units of the time series itself. They could be scaled or standardized in some way. They could be percentages and so on. So all the evaluation methods may not be in the same units. Therefore, comparisons of forecast error occur within a method. For example, in this case, it's the colored columns, or between methods that use the same unit or scale. So you could have forecast errors that are in the original units. You could have some that are scaled in some way. You could have some that are percentages. Now, of course, you can't really compare those apples to apples. So you're comparing within a method and then looking across where the best one might be in a given forecast method. Now, it's very common for methods to disagree about which is the best method for forecasting. So in this matrix here, forecast method C could have the lowest error in evaluation method 1, evaluation method 2, and evaluation method 3. Then we could say forecast method E is best in evaluation method 4. And we could say that forecast method A is best for evaluation method 5. So it is very common for methods to disagree about which is the best method for forecasting, and it will be up to you as the analyst which to use for future forecasts. Sample forecast accuracy matrix. So here we put in some more details. In the left-hand column, we have 5 forecast generating methods. So the Naïve method, moving average, weighted moving average, smoothing, exponential smoothing, and ARIMA. So ARIMA is actually a modeling method, but I put it in here because many people know about it. Across the top, we have accuracy measures, or accuracy methods. So MAE is mean absolute error. It's also called mean absolute deviation, or MAD. We have MSE, which is mean square error. Some of you might have heard of that before. We have MAPE, or MAPE, which is mean absolute percentage error. Then we have SMAPE, which is symmetric mean absolute percentage error. Then we have MASE, mean absolute scaled error. So those are all ways of measuring forecast error, and we pair them with different forecast producing methods. Let's look at a genuine example, Nigerian GDP, using the Naïve forecasting method to predict GDP per capita for Nigeria. So a few notes on GDP to give you some context. GDP stands for Gross Domestic Product, which is the total economic output of a given location or geographic area. Could be states, territories, usually it's countries, could be continents, or even the entire globe for that matter over a given time period. So GDP per capita is a ratio of GDP divided by a population, which helps with scale and comparisons. It's GDP per person. Per capita measures are very helpful because it keeps, in this case, large countries with many people engaging in economic activity from dominating GDP measures. So when we do it per person, then we scale it to a per capita basis, and it's easy to compare one with the other. So GDP enables policymakers and central banks like the Federal Reserve, which is the Fed, the European Central Bank, or the ECB, and there are many other central banks, to judge whether an economy is contracting, a recession, or booming, it's overheated, and promptly take necessary action, usually through the adjustment of interest rates, by the way. It also allows policymakers, economists, and businesses to analyze the impact of variables, such as monetary and fiscal policy, economic shocks, pandemics, as we all know, and tax and spending plans. And GDP can also be an indicator for potential investors. So if companies or other countries are looking to invest in a country, they might look at that country's GDP per capita to see if it's growing or declining or stable. Here's our example. On the left in this table, we have Nigeria's GDP per capita in constant US dollars from the year 2000 through the year 2020. Constant US dollars means they have been adjusted for inflation, so the numbers won't naturally increase as inflation increases. So we can see that in the year 2000, Nigeria's GDP per capita was $1,451. So $1,451 per person. Now, if you look at the chart, by 2014, 2015, that had almost doubled. So in 14 or 15 years, Nigeria's GDP per capita almost doubled, which is pretty extraordinary. If we graph it, it looks like this. So we can see that a steady increase from 2000 all the way up to 2014, 2015, then a slight decline since then. Of course, a lot's been going on since then, so it's not all that surprising. So we can see the general pattern of Nigeria's GDP per capita over this 20-year span. Now the question here is, how might we approach making a forecast for the year 2021? So our data ends at 2020. We want to make a forecast for 2021. How might we do that? So we can see an up and then down pattern. And the questions we can ask, some common sense questions we can ask are these. 1, do we expect Nigeria to continue to even have a GDP per capita going forward? Now, of course, this question in this case doesn't make a whole lot of sense. It's sort of a nonsense question. But in other contexts for time series, this is a very real question. Measures can stop being taken. Something can happen where the measure no longer exists, or another measure replaces it. In this case, this question is not all that relevant, but it's something to keep in mind in other contexts. 2, what factor or factors might cause changes in GDP per capita? So an economic output change or a population change. Now, I'm not talking about other external factors. I'm talking about the factors inside the ratio of GDP per capita itself, economic output or population. So of course, GDP per capita could decrease significantly if economic output goes down, or that remaining constant if population increases. Likewise, the reverse could be true. So what factors inside the ratio itself could cause changes in GDP per capita? So if so, will we expect the measure to decline, say, to $500 per person in 2021, down here in the lower right? Is that probable? Well, I guess it's possible, but not all that probable. There's nothing here to indicate in the time series data we have that this measure will go from almost $2,500 per person down to $500 per person in 1 year. It's possible, but not probable. How about increasing to $3,000 per person in 2021? Is that probable? Well, it's definitely possible, and it's much more probable than going down to $500. But again, in the time series data we have, there's nothing to indicate that this tends to move that drastically over a 1-year period. So it's probable, but not likely. So what has been the recent trend for Nigeria's GDP per capita? Has it been increasing, decreasing, or flat over the past, say, 10 years? Well, we can see here that it was increasing. It kind of peaked around 2015, and then it kind of went down a little bit or remained flat sort of since then. So we can get an overall sense for the recent history of this time series. Now, based off the recent past, just by looking at it, what might a good guess be for GDP per capita for 2021? Just using your common sense, using your eyes, looking at this chart, what might be a good guess? I might guess it's somewhere in here. Now, I'm not going to, nor should you ever, make a point forecast or an individual number forecast into the future. It should always be put in some interval. So here, I'm going to put this interval in these green dots and say, well, just based off common sense, looking at this graph, I think that's a likely location for 2021 to occur. The naive forecast. The most basic or baseline forecasting method is called the naive forecast due to its simplicity, often treated as the null or baseline forecast. The naive forecast predicts that the next value in the time series, the unknown, will be the same as the last known value. So for example, using my home, if I used 30 kilowatt hours of energy yesterday, I would predict to use 30 kilowatt hours today. That's the naive forecast. Now, in the case of Nigerian GDP per capita, since 2020 was $2,396, the naive forecast for 2021 will be the same value, $2,396. Naive forecasting works best for flat or horizontal stable time series, and we'll see that here in a second. Now you might be thinking, Naive forecasting is way too simple to ever be the best forecasting method. Well, that thinking would be incorrect. Just because something is simple does not mean it cannot be the best method. So mathematically, it looks like this. This is very simple. The forecast, F, for the next time period, which is t plus 1, is equal to the actual value for the current period. So a few quick examples. A small business has 10,000 euros in sales today. The naive forecast would predict 10,000 euros in sales tomorrow. Suburban passenger traffic in railways across India was 4.78 billion in 2019. The naive forecast would predict 4.78 billion in 2020. Twitter had 321 million monthly active users in the fourth quarter of 2018. The naive forecast would predict 321 million monthly active users for first quarter 2019. Now note that these are all different time scales. The first one is daily. The second one is annually or each year. And the last one, the Twitter example, is quarterly. It doesn't matter. As long as the time period is consistent, we can use any time period we want. Forecast error. So forecast error is simply the actual value minus the forecasted value. If you have trouble remembering that, just remember the A comes first. A small business has 10,000 euros in sales today. A naive forecast predicts 10,000 euros tomorrow, but the actual sales were 10,700 euros. Therefore, the forecast error is 10,700 minus 10,000. So that is the actual value minus the forecast value, and that equals 700 euros. That was an under forecast because the forecast value of 10,000 euros is less than the actual value of 10,700 euros. Suburban passenger traffic in railways across India was 4.78 billion in 2019. A naive forecast predicts 4.78 billion in 2020, but actual traffic was 4.6 billion. Therefore, the forecast error is 4.6 billion, the actual value, minus 4.78 billion, the forecast value, which is negative 0.18 billion. That's an over forecast because the forecast was over the actual. Twitter had 321 million monthly active users in Q4 2018. Naive forecasts would predict 321 monthly active users for Q1 2019. However, there were 330 million monthly active users in Q1 2019. Therefore, the forecast error is 330 million minus 321 million, which is a difference of 9 million. Again, an under forecast because 321 million, the forecast value, is less than 330 million, the actual value. Notice that an under forecast error is positive and an over forecast error is negative. Under forecast means our forecast was too low and the actual value overshot it. Therefore, the actual value is larger and therefore the forecast error is positive. And the reverse is true for under forecasting. So here is how the naive forecast works in a chart form. So here we have our data we had before on the left in the first two columns. The naive forecast is in the third column. All we do is take the known value from the previous period. That becomes our naive forecast for the next period. Notice that there is no naive forecast for the first period because that's where we start. 1451 was the actual value in 2000. So our naive forecast for 2001 is 1451. We repeat this process for the entire table. So we just shift everything down 1 in the naive forecast. It's very simple. Then we measure the accuracy. So the forecast error is simply the difference. So in 2001, the actual was 1,499. The naive forecast was 1451, which obviously came from the year 2000. The difference between the actual and the forecast was $48 in this case. So for 2002, the actual was 1686. The naive forecast was $14.99. Of course, that came from 2001's actual. The difference is $187 per capita. That's a huge error. Well, why is that? Look at the data in the GDP column. We can see there was a huge jump of $14.99 to $16.86 from 2001 to 2002. That is why that error is so high. Then we go on down the table, we can see a big error there in 2004. Same thing. There was a big jump from 2003 to 2004. Same thing down in 2009 and 2010. Then we get down to 2014, 2015. our errors turn negative. Well, why is that? The trend changed. Remember from our graph that the trend started to go down and our forecast errors turn negative. Let's talk about that more here in a sec. So here's our table from before, and here's our graph. So here is the actual GDP per capita, and then here in the pink line is our forecast using the Naïve forecast. What do you notice? Well, it's the same graph, just shifted forward one time period. That's what the Naïve is pretty simple. That's why it's easy to understand, actually. We just shift everything forward one time period. Then we have sort of one on the end. We just don't write that. As I was saying before, a series of positive Naïve forecast errors, the under forecast, indicates an upward trend in the series. So the forecast cannot keep up with the upward trend. Therefore, we have a lot of positive Naïve forecast errors. You can see that in the graph. The per capita GDP in green is always above the forecast, there in pink, because the trend is upward. Then we have a series of negative Naïve forecast errors, or under forecasts, indicates a downward trend in this series. So again, the exact opposite. So when the trend goes down, the Naïve forecast is always sort of catching up one time period. Therefore, the errors turn negative. And there's also one more important thing on this graph that's not here in the text. Where in this graph do the GDP per capita in the green and the forecast, Naïve forecast in pink overlap? Well, it's right where the GDP per capita is at its flattest. So what is the forecast GDP for 2021? Well, in this case, we go up to 2020. That's $2,396 per capita. So that goes into the last cell in the last column. What is the actual GDP for 2021? Well, this data did exist. I didn't tell you before. It does exist. And it's $2,422 per capita. So that's our actual value of 2021. What is the forecast error for 2021? Well, it's actual minus forecast. So 2422 minus 2396, and that is $26 per capita. So again, it's positive. So what does that mean? Well, that means our forecast was under because it's actual minus forecast. The forecast was too low, the actual was higher, and therefore the error is positive. What is the forecast GDP for 2022? Well, we go to the actual for 2021, which is $2,422 per capita. And finally, here's our chart again. Remember this from before? Here is the GDP per capita, and there are my lines on my guess from the previous slide from before. It's an exact copy. So where is the actual for 2021? Well, it's right here, $2,422, which is right within the sort of eyeball range that I put in my educated guess. So this video is just the beginning of several that will look at many different forecasting techniques and evaluation methods. So please like, comment, and subscribe for more videos. Thank you for your time, and I hope you found this video helpful. Take care and bye-bye.